All right, calculus. This is the beginning of section 5.4 on the fundamental theorem of calculus. With a name like the fundamental theorem, you'd think it'd be pretty important, and in fact it is. The fundamental theorem of calculus really is going to take the two big concepts in calculus, the derivative and the integral, and it's going to tie those ideas together in a really beautiful and useful way. So, the lesson I'm going to teach on this subject is going to be, I'm going to try to help you understand how these two things are related. And in order to really get that, I think it's going to be useful to have the idea of position and velocity as like an example that we can refer back to as we discuss the ideas of the section. So I'm going to start with talking about position and velocity and introduce the introduce a concept of net change and displacement through this subject. So let's talk about S of t and V of t. Let's suppose that we're going to do an integral, a definite integral of velocity, okay, from A to B. We know that the velocity is the derivative of the position. So the integral of velocity should have something to do with position, given that the idea of an indefinite integral is like the opposite of a derivative. It's an antiderivative. So how does a definite integral relate to this idea? Well, let's look at a picture. Let's say here is your graph and here's time, and then here's our velocity function, right? Let's say this is our v of t function here. And here's our interval, a to b. What we're doing, remember, is we're breaking this interval up into lots of little rectangles, right? Lots of little subintervals, and we're building a rectangle. Let's zero in on one of those little rectangles right there. Okay, so I'm going to take this and I'm going to kind of look at one of those little rectangles. We have our time axis down here, and to the left and right side of that little sub-interval are called ti minus 1 and ti. So this would be the ith. We're looking here at the ith subinterval. Now, on top of this subinterval, we have a rectangle, and the height of that rectangle roughly corresponds to the velocity on the subinterval. The actual velocity on the subinterval is not constant, so it wouldn't be a flat function up here. However, we're basically treating it as if it is constant, okay? Because we're using that rectangle to approximate the area under the curve. If you look right here, you'll see the height of the rectangle and the actual height of the function are not going to be in agreement with one another all the time. But remember, we're going to be taking a limit as delta x approaches 0 and n approaches infinity. So the difference between the function and the height of the rectangle is going to be negligible in the limit. So we're basically essentially treating the height as our velocity, acting as if that distance is, as if that velocity is constant on this tiny subinterval. So here's our time, right? So what we're doing is, when we take a definite integral, is adding up all these areas. And for one of these little sub-rectangles, the area is equal to width times height, right? So that would be velocity times time. Now, let's just think for a second. Let's go back to what we know about like constant velocity. If you have constant velocity, if you multiply that by like the elapsed time, the amount of time that passes, what you get is basically, something like meters per second times seconds, right? And the seconds cancel out. It's the speed you're traveling times the amount of time you traveled for. This gives us the distance traveled. So that would be the distance traveled on that short interval, right? On that short interval of time from ti minus 1 to ti. So what we're getting is we're adding up all these areas. We're adding up all these little values that basically represent the distance traveled. So we're adding up all these little short distances to get a total distance traveled. So what we're seeing here is that the integral from a to b of v of t with respect to t is going to be the net distance traveled. Okay, if the object is moving forwards and moving backwards, sometimes when the object moves forwards, it's going to have a positive velocity. Then it moves backwards, it'll have a negative velocity. So overall, we are treating the positive velocity as like a positive area, distance traveled in the forwards direction. and the negative velocity would be like a negative distance traveled. Okay, so that's why it's net, right? This is relating this back to this idea of net area with positives and negatives. We have net distance traveled. That means that what this really is, another word for this, is displacement. It's not really the total distance that you've traveled on the interval because when you travel backwards, we're subtracting instead of continuing to add that distance. So it's, with that net distance traveled, the better word for that is displacement. And displacement is something we can calculate in a different way. Displacement can be calculated by taking the position at the end minus the position at the start. And this idea, the idea that this is displacement, and we're taking the difference in positions from the end and the start, this is getting us closer to the idea of the fundamental theorem of calculus, because here we have the integral of velocity, and the velocity is the derivative of position, and it turns out to evaluate that integral of velocity, all we have to do is take the final position minus the initial position. Okay, this is, we're getting closer, because now we're seeing some relationship between derivative and original function. So this generalizes to something called the Net Change Theorem. And the Net Change Theorem just says that if you have some function capital F, if that is a quantity, some quantity, and capital F prime is its rate of change, then what we can do is take an integral from a to b of the rate of change, f prime of x, with respect to x, or it could be with respect to t. If you want to, if this is changing with respect to time, we could just do this dt instead. But the integral of the rate of change is going to equal the quantity, the final quantity, f of b, minus the initial quantity, f of a. This is called the Net Change Theorem. And in some respects, this is sort of like an application of the fundamental theorem of calculus. So I'm going to then, in the next video, show you how this relates to part of the fundamental theorem of calculus. I don't know, I'm just kind of sketching random shapes over here. And then we're going to do some examples so you can see how this theorem and its sort of analogous idea, the more general fundamental theorem of calculus, is going to make evaluating definite integrals much, much easier for us.